So in this video, we are going to play a bit with what we learned up until now. And in order to do this, I do have prepared a couple of exercises. Now I want to remember to you that you can find the exercises and in general all the code of this course by going on GitHub and searching for Michele Nuzzi slash Plutus oriented Haskell, and you'll find the exercises into an exercises folder. And in this case, we are going to do the exercises from the Haskell basics section, and you'll find the two exercises of this video and also the solutions. But I'd suggest to you to try to solve the exercises without looking at solution. And with that being said, we can start with the first exercise. And as a first exercise, I would like you to implement a function that takes a function from a to a boolean and a list of a's. So we know that the elements of this list are valid inputs for this function, and returns a boolean, and the function is called trueForAll. So it must be true if all the elements of the list returns true when provided to this function, and false if any of the elements returns a false. So you should have all the instruments in order to define such a function. So you can now pause the video and try to solve this exercise yourself. So I assume that you have paused the video. Therefore, I'm going to show you my solution, and my solution does use pattern matching. And when we got a list that is an empty list, then we do not have anything to test, and therefore we just return a true, and we do not use the function. So I put an underscore here in order to tell GAC that this is intended. And instead, when I do have a list that does contains at least one element, I do need the function, and I want this call to be substituted with the following expression. And the expression is to use the function we got with the first element of the list, and then perform a logic AND with whatever is the result of calling trueForAll on the rest of the list with the same function we got. And let me also show you a cool thing that Haskell is capable to do, and this is due to the lazy evaluation of Haskell. First of all, Haskell does have a function very similar to the one we just defined, and it is called AND, and we can ask for the type of AND. And of course, well, this foldable is just a way to indicate a list or some type that can be similar to a list. In any case, we will consider this to be a list. And so here we are saying that this is a list of Boolean, and AND is a function that, given a list of Boolean, returns a Boolean, and using as an example, and with 3 true returns a true, but if even one of these 3 true is false instead, it returns, of course, a false. And I want to show you a feature of Haskell that leverages on the lazy evaluation of Haskell. Now, in Haskell, it is possible to define infinite lists. As an example, I could define a list that I'll call ones, and I define ones to be one added to a list of ones. And since this variable is holding the expression itself and not the result of the expression, this is what lazy evaluation means. This statement is valid in Haskell, but when requesting to evaluate it, it will of course go on forever without ever returning. But we can use a function defined in Haskell, which is take. And take is a function that, given an integer and a list of anything, returns a list of anything. And what it does is taking a list of length of the number we provide. So if I say I want to take a list of length 2 from a list that does contains 5 elements, I of course, only get the first two elements. And so I could ask to take 10 elements from the ones list, and I will get 10 ones. And I want to use this ones infinite list to generate an infinite list of truths. And this is still, of course, possible. And of course, we can see that this list contains all truths. And the reason of why I do have created this infinite list of only true values is to show you the lazy evaluation also when calling a function similar to the one we defined. And here I'm calling the hand function with as argument a list created from this list concatenated with the infinite list we just created. And this list contains two truths and one false. And if we launch this expression, we see that we return almost immediately false. And that's because we don't really need to ever evaluate this infinite list of truths, since doing the AND with true and true returns true. So we must check the next value, and the next value is false. So true and false is false, and we know for sure that whatever follows will be false. Therefore, we immediately return a false. We never evaluate this infinite list. And that's something that is possible thanks to the lazy evaluation of Haskell. So for the second exercise, I would like you to implement a function that takes as argument a list of positive integers and returns the maximum element of this list. And you should already have all the instrument in order to implement such a function. So please now stop the video and try to solve the exercise yourself. Well, I assume that you have paused the video and solved the exercise. So I'm going to show you my solution. And the solution that you should have written should be similar to this one. Of course, also one using guards would have been totally fine, but yeah, similar to this one. And in this solution, I do use pattern matching in order to recognize when I do receive an empty list as argument. In that case, I just return a 0 since we are working with positive integers. If I do have only one number, then I just return that number since we don't really have anything to compare it with. And in the case the function does have more than one element, then I compare the first element with the max element of the rest of the list. And of course, if that first element is greater or equal than whatever is the max of the remaining part of the list, then we just return the first element. If that is not the case, then we return the highest element of the rest of the list. And this implementation works, but we do have a little problem. And the problem is that we call this findMax recursively twice inside this body. And this is bad since in the worst case scenario, where we do have the max element at the end of the list, then we always enter this second branch of the if else statement. Well, in this case, this function has an exponential time complexity, since for each call of the findMax, we will be calling twice that same function inside the body, one when evaluating the condition and one when we will need to return the maximum element. And since we do this call twice for each call, also that call will do twice a call to themselves, and that is true for also those calls. So the longer the list we get, the more recursive call we will do, and the number of recursive call that we will do in this worst case scenario where the max number is at the end of the list will be 2 to the length of the list, since here we'll do 2 call, here 4, here 8, and so on. And this is exactly the definition of an exponential time complexity function, and this is usually a bad thing. And in order to prevent this kind of behavior, we may want to store the result of this function call inside a variable, and we can declare variables inside a function by using the where keyword right after the expression with which the function call will be substituted with. And the where keyword allows us to open a block at the end of the function definition that allows us to declare variables that, of course, are local to the function. So, as an example, I cannot use this restmax outside the findMax with partial result function. And in this particular definition, I'm using the restmax variable to hold the recursive call to that same function with the rest of the list as argument. But even with this partial result, the problem is not yet solved due to the lazy evaluation of variables in Haskell. In fact, this restmax variable is not directly holding the result of this function call, rather is holding the expression of this function call. So when using restmax inside this expression, we are effectively substituting restmax with this expression here, and we do not really have any advantage of writing the expression directly. Therefore, the problem is still present. And in order to really fix this problem, we would need to store the actual result of this function call inside this variable rather than the expression that calls the function. And we can do this in Haskell by using this extension that I'm enabling right up here on top of the file. And this line is just telling to the compiler, in this case GAC, that I'm going to use this extension inside this Haskell file. And this particular extension is called bank patterns. And bank patterns are used like so. In particular, we use exclamation mark in order to use a bank pattern right before the name of the variable that will load the result of whatever expression we do have here. And in this function definition, I'm using the let in keyword, and those keywords are really similar, if not equal, to what is doing where. The only difference is that when using let in, we have to put the block of declarations right before the expression that will substitute the function call. But apart this detail, there should be no difference between the where keyword and the let in keywords. Both allow us to declare variables, and the only difference, therefore, between this declaration and this declaration is this little exclamation mark right here, which is forcing the evaluation of this expression, therefore storing the result of this expression inside this variable and not the expression itself. And so, back to this particular case, here we store the 20, which is the max value of the rest of the list, and not this call. So inside this expression, we do not have two calls to the findMax optimized, but we do only call once when storing the value, and then substituting the value when we encounter the variable. And this drops the time complexity from exponential to linear. And we can actually see this in action by calling findMax, which is defined with the recursive call done twice. So this is the version with exponential time complexity, and we see that calling this function takes a while to be completed, whereas calling the optimized version, which is this one with the bank patterns, is completed almost immediately. And we can really appreciate the difference between exponential and linear just by adding 10 to the length of the list. And we see that this is keep going and still has not returned anything. And I'm just stopping the process because I don't really know when that function will ever return. Whereas by calling the optimized version with a list of length 30, we see that it returns immediately. And this is a really important difference between exponential and linear time complexity. So in this video, we saw what are the pros of the lazy evaluation of Haskell, but also what can be the cons of the lazy evaluation of Haskell. We also saw how to declare local variables inside a function definition by using both the where keyword or the let in keyword. We introduced our first extension, which are bank patterns, and we saw how this particular extension is useful to force the evaluation of some expression. So if this video was useful to you, please consider to subscribe to the channel and also to like the video. If you really want to support the creation of this content, you can delegate your ADA to Harmonic pool and earn interest on top of supporting this series. You'll find the link to do so in the description below. In any case, I want to thank you for your time. Remember to stay decentralized, and I will see you in another video. Bye bye.